In this example, we're going to look at a Bakken oil producer. This is a long lateral multi-stage fracture well, flowing oil well. When dealing with oil, we can use a lot of the same analysis techniques as for gas. Linear flow is really not all that sensitive to whether it's an oil well or a gas well. The properties are pretty much the same. One thing that we do need to pay attention to in oil wells is the producing gas-oil ratio. And specifically what we're looking for when we're looking at GOR is to ensure that it remains constant. During linear flow, the GOR will usually remain constant. So what I'm going to do here in Harmony is just plot GOR on here, and indeed we can see the GOR remains flat, and its value is also important because that can give us an indication of where the bubble point pressure is in relation to the reservoir pressure. In this case, it looks like we're in the neighborhood of about 1,000 standard cubic feet per barrel for solution gas-oil ratio. If we go and look at our data, we will see that at the correlations anyways predict that at 1,100 standard cubic feet per barrel, our bubble point pressure is about 3,000 psi, which is well below the 8,300 psi of reservoir pressure that we have. And that will usually be the case in these examples. They're very tight. Reservoir pressure is high. We're not going to be drawing the reservoir pressure down except locally very near the fracture face. So largely the bubble point pressure in the reservoir will remain in the undersaturated condition above bubble point pressure. So we're going to go and take a look at this example. And again, I'm going to start with a Fekete type curve. This is an excellent way to do preliminary diagnostics on the data to get a sense for whether we're looking at a boundary dominated flow example or a transient example. When we look at this data, we can see that the shape of it seems to approximate boundary dominated flow, but is somewhat shallower in decline than the limiting decline curve for boundary dominated flow, which is the harmonic decline curve. So indeed, the conclusion here would be that there are some transients, if not completely transient flow. There is some transient flow going on in this example. If we zoom in, we can see more clearly that the data does go up above that harmonic stem, which would indicate that we do have some transient flow going on. To check this again on a different diagnostic plot, we'll look at Wattenberger. And the Wattenberger plot confirms our suspicion and shows very clearly a half slope on both the derivative and the normalized rate, indicating that we have linear flow. One thing of interest here is if we look at the red data points, these are the normalized rates. They are very close to matching on the type curve, which suggests that there's not a whole lot of damaged skin in this well. We're going to go and look at the unconventional oil module now. What we're expecting to see on the top left-hand plot, which is our square root of time plot, is a straight line. And so we can adjust this, and again, keeping in mind that this line has to go through the origin or above. In this case, it doesn't look like there's very much skin damage. The data seem to point straight to the origin, which indicates a very good completion efficiency. And we have our straight line here. There is some scatter in this data, which makes it a little bit difficult to pick out that central trend. One way that we can do that is by doing a best fit of the data. So if we go through and select our data, we can kind of work out what that best fit line is. Unfortunately, it put that line through a negative intercept, so we're going to want to shift that upwards to make sure it goes through 0. And that's not too difficult to do. So if we do that, maybe adjust the shape of the line again. We just need to make sure that that line goes through the origin. One way to help do this is if we put the the pivot point or the red dot right at the origin itself. And then we can ensure that that always goes through the origin, then we can pick our straight line from there. Okay, so we have something approximating a straight line fit here. This straight line, of course, gives us the cross-sectional area square root of permeability product, and we can also get XF square root K from this. If we look at the right-hand side plot, this is our flowing material balance plot. As expected, this plot does not make a straight line because it's still linear flow. So what we're extrapolating here is the minimum contacted oil in place, and we know that we're getting the minimum oil in place by ensuring that the green dotted line goes through the end of the data. And so there we have it. We have oil in place of approximately 2 million barrels, which works out to a drainage area of the stimulated reservoir volume of 145 acres. On the type curve plot below, you can see we have a good match of the data there, and then we have our production forecast shown here. This would be a good P90 forecast in this case. Reason being is we're going with the minimum size. The other piece of information we can add in here is if we put in the well length and the number of fracture stages, which in this case is 12, it calculates a matrix permeability for us. Again, this matrix permeability is not necessarily a unique number. The assumption here is that we have seen the boundaries already, which of course is just a minimum oil in place. If in fact we have some additional information about matrix permeability that we can enter that here and actually calculate what the expected drainage area would be. For example, let's say that we had some core analysis that told us that our matrix permeability was 500 nanodarcies. If that were the case, then we would have something like this. And our drainage area would be somewhat larger than the minimum. Our dotted green line is sitting out here now, and now we have a composite decline curve analysis with a b-value of 2 going up until the end of transient flow, and then transitioning into a lower b-value after that. Now for our boundary dominated flow segment of the decline curve, we should probably use a b-value that's lower than 0.5. Since this is oil, we're going to use 0.3, which is a reasonable number to use for solution gas drive. Now what we're looking at here would probably be best described as a P50, and it really hinges on our assumption of matrix permeability. If we really don't know what the matrix permeability is, then we would probably want to guess at the stimulated area, maybe based on well spacing or something like that to get a P50. But this would be a good P50 number. If we're happy with this number, we can then put in oil decline curve, rate versus cumulative plot, and display our information on there. Display our forecast on there. So there's our oil curve, and I'll put my unconventional simplified analysis on there, and there we have it. This is much more robust than simply doing a decline curve based on a best fit of this data. It has some actual physics built into it. It takes into account some knowledge about matrix permeability for this reservoir and is much more defendable to reserve auditors.